Thanks a lot, David, for a fantastic talk. My name is Sachin Chitta. I'm from Willow Garage, and I'm actually representing a huge motion planning community that works on the motion planning components in ROS. And this talk is together with my colleagues, Ioan Sucan and Gil Jones, who are both sitting on this side. So Ioan's going to give part of this talk. I'll start off and he'll give part of the talk. So what am I going to talk about? A lot of you know about the motion planning stacks in ROS, and you're probably already using them. But there's probably a lot of you who don't know exactly what they do and what you can use them for. And the idea behind this talk is to give you information about what you can do with all the tools that we have in ROS. And I'll show you some examples of things that we've been able to do so that you can see how you can take these things and apply them to your own robots. So sort of the traditional definition of motion planning is you're trying to plan and execute motions for a robot under a given set of constraints. And the typical set of constraints that most of you are familiar with are collision constraints. So you're saying, I want the robot to get from point A to point B without colliding with anything. But there's other sets of constraints that we can deal with as well, which we'll talk about as we go through the talk. So here's an outline. I'll talk about the past results we've had and sort of the success stories, mainly briefly about the base navigation stack, which is probably the most familiar stack for most people using ROS with mobile robots. I'll talk about the ARM navigation stacks, the tools that you can use with these, and then my colleague, Ioan, will introduce you to the future. So the ARM navigation stacks are basically the ROS components that you would use to do motion planning for manipulators. And we started this effort almost, I think about 4 years back, almost 4 years back. And the idea was to develop a set of stacks, a set of capabilities so that you could use motion planning on the Pier 2 robot. That was our initial focus. And our current approach, we have, so the meat of these stacks is, of course, the motion planners. And we have, as we've gone through the years, we've tried different approaches. So we have 3 different approaches that you can now use. One is the sampling-based planners, and these come from the OMPL library. This comes out of Lydia Kavraki's lab in RICE. There's the search-based planners, which come from, which are in the SBPL library, and they come out of Max Likachev's lab at CMU. And stochastic trajectory optimization approaches, again, one of them coming from CMU, and the other one was a joint Willow USC effort. And so you can see from, I'll just let the movies play again. So you can see from these movies some of the things that we've been able to do with these stacks. Our primary goal was pick and place. So we wanted to be in sort of unstructured environments with different kinds of objects and try to pick them up and put them down effectively. And this is our current state of the art. It's the ROS manipulation pipeline. This is work at Willow with Kaijin and Mate, who a lot of you know do a lot of our manipulation and grasping work. So we call this the manipulation or grasping pipeline. And what this movie shows you is sort of the entire flow of what's going on with the manipulation pipeline. I'll just let it start again. So it starts off with the perception parts. So we're taking in raw sensor data from all the sensors on the Pier 2 robot, and we're trying to build up a consistent representation of the environment. And There's a lot of little things you have to do to get this right. Data from sensors is noisy. You have to filter it. So we're taking out, for example, the arms of the robot itself, which occlude these sensors. We're building up an environment using a package called Octomap. This comes out of the University of Freiburg. We're doing segmentation and recognition, and this is based on in-house object detection routines. So basically, the robot is building up this continuous model of the world. Once it does that, it figures out grasps. And there's two ways of doing this. Either we can do it online, just using the point clouds themselves, or we do a lot of stuff offline for certain objects using a software called GraspIt, which comes out of Columbia University. So using a combination of all these, we can build up live a representation of the environment. We can generate grasps, and this is where the motion planning comes in. Once you have the grasps, you say, how do I get to and execute these grasps? And that's where the motion planning pipeline it finds its main use. So this demo that you're actually seeing is sort of our standard demo that we take to conferences, and here the goal of the robot is basically trying to move all the objects from one side to the other side. And this demo has been expanded on, and it's been used on multiple robots now, and it's fairly robust. And there's, in addition to all these elements, there's also a set of little things that we do, particular problems that we can address. So one of them is constraint planning. So a lot of times when you're doing motion planning, when you're moving objects around, you want to keep them upright. And this is one of the things, the additional constraints, apart from just collision constraints, that you can impose on a motion planner. We want to be robust to sensor uncertainty. We want to be robust to errors in object detection. So our grasping is actually reactive in the sense that it can actually correct in a lot of cases for any error that you detect the object wrong, or you don't know exactly where it is because your calibration is off, and you can deal with all these kinds of things. The stack that you are most familiar with, and this comes out of work at Willow by Ioan, Marder Epstein, Brian, Tully, and Kurt, and a lot of people, is the 2D navigation stack. I think this stack has now been ported to tens, if not hundreds of robots. It probably is the most widely used component in ROS right now, and that is Ken a while back. He didn't really believe the robot could do that, and he was testing it out. So it's one advantage of being at Willow is that we test our robots and our algorithms very hard. It's a hostile environment for developing robot code. So that was the 2D navigation stack, but as we started doing, we started moving towards more mobile manipulation tasks, and as we started doing that with the Peer 2 robot, we realized the 2D navigation is not enough for a few things that we wanted to. So this is one example where the robot sort of has to slide under a table so that it can put things down. And you can imagine if you're using a projected 2D map, this is actually not possible. And this is some work we did last year. So Armin and Mike Phillips. Mike's not here, but Armin is here somewhere. Oh, there he is. Armin's from the University of Freiburg, and he worked on what we call the 3D navigation stack. So what you see here is a representation of one of the Willow labs in Octomap, which is the software that Freiburg developed to represent large areas using octrees. And basically what we're doing here is doing full 3D collision checking so that we can deal with tasks where the robot needs to get closer to obstacles and actually manipulate obstacles. So in this case, the robot has to move a laundry basket from one part of the room to the other. And over here, we're using the SBPL library for all the motion planning. And essentially, if you've done collision checking, you'll know that full body 3D collision checks are expensive. So we came up with some neat different ways of doing it, some hierarchical ways of doing it, so that we would not have to do 3D collision checks most of the time. And the robot had to get through a fairly constrained environment, and we deliberately set it up so that it had to do that. And you can see that it was pretty successful in getting through the set of chairs. And you can also see it sort of looking around to see which direction is going in. So the intention of showing you some of these demos is to give you an idea of what you can do with the set of capabilities that we have in ROS right now. So all the ARM navigation stuff is in electric, it's in Forte, and you can use it. The 3D navigation stuff is also there, but we're working on improving it, and we should have it out later. So we did a lot of this effort, and in the beginning, we were doing a lot of stuff with the PR2 robot. That was sort of our sole robot that we had in-house to do stuff. But we were always aware of the fact that other people would want to use this. And from the beginning, we tried to keep our stacks as generic as possible. We tried not to make them very PR2 specific. And this is some work, actually, that Gil Jones did. He's in the corner over there. This is the ARM navigation wizard, and basically what this helps you do is port all these stacks to your robot. So basically, you get the URDF for your robot that David just described, and that's the input to the stack. You can define chains, you can define certain collision properties, and you can create, you can sort of auto-create all the configuration files that you need to run the motion planning stacks on your robot. And once you do that, you can test these out, again, in a tool that Gil and his interns wrote, in a tool called the Warehouse Viewer. So this is basically a simulated environment in which you can test out motion planning. So you can basically ask the planner, what are you going to do? You can actually visualize it and test and look at it before you start doing this on the robot. And this can directly connect to the robot as well. So in this, you can create worlds, simple worlds. You could create motion plan requests. So you say, I want to go from here to there. You can log all this. You can store all this information and retry it later. You can introspect into different parts of the pipeline. And these two tools, I think, have made the ROS motion planning stacks really portable. We've seen a lot of people actually use these to port our capabilities onto their robots. And if you want more information on this, we did a tutorial at ROS last year, and there's a pretty extensive documentation on that website that you can look at. So look for the tutorial document, and that gives you a step-by-step way of going through these tools and getting these things applied on your robots. I think our slides will be up on the website, so you will be able to get this information later as well. So we took all this. Where's Sean? Oh, okay. Sean Edwards is in the back, and so Sean Edwards came down from Surrey to Willow Garage to teach us how to make good videos with music in them. No, he actually came down to see what we were doing with our manipulation stacks and apply it to industrial robots. And it was actually a fantastic effort. So this is a joint collaboration between Swery, Yasukawa Robotics, and Willow Garage. And a lot of people at Willow were involved in this as well. And essentially, it took a lot of the capabilities that we had and ported it onto this modem and ARM. You can see that there is a different hand also on the ARM. I won't speak too much about that, but we can also, generate graphs for these new types of hands. So this is a Robot IQ hand, and you can use our software that way too. So the other part that we did is just this was just last week. We did the ICRA Mobile Manipulation Challenge, which was sort of an application of everything that we wanted to do. So in this case, the robot was supposed to act like a waiter in a typical sushi restaurant. So it had to clear tables, pick up things from tables, set tables. It had to pick up things from a rotating turntable. And this really pushed us from a lot of the tabletop manipulation things that we've been doing so far into actual mobile manipulation. And this is one of the thrusts of what we're going to do in the future. We want to be able to do stuff where the robots are actually moving around and manipulating things as they do that. So a lot of these videos will be online soon, so you can see all this. With that, I'm actually going to hand over the mic to Ioan Sucan, who's going to talk about our future efforts. After he does a little bet that I had with him, so.
Come on.
How did that happen? Sorry.
Clearly, this is not going to work. So that's okay, because I forgot my dancing shoes home. So don't worry about this. There goes my bonus, yes.
I like to move it, move it. I like to move it, move it. You like to move it.
All right.
I like to move it.
So with that said, I was actually supposed to do a dance here because I always make Sachin show this video whenever he talks about Move It. So he said, okay, I'll show it, but the next time you talk about it, you're going to dance. Unfortunately, Sachin, I'm really sorry. I forgot my dancing shoes home. So, so I'm going to talk about current and future efforts in motion planning in ROS. All right, so can you hear me? So Move It is really an evolution of the ARM navigation software stack. We learned a lot developing the ARM navigation software stack. We made a lot of mistakes. Lots of things were good. And now we're trying to incorporate the lessons we learned and develop a piece of software that is better from a software engineering point of view, and it incorporates new capabilities, solutions to problems that we found and understood while developing the ARM navigation stack. So what we're trying to get is a package that is intended to help developing applications that need motion planning. And this package should be efficient, it should be generic, it should be easily extendable and robust. And I'm going to go into a little bit of detail on each of these attributes, and feel free to ask questions. So what is Move It? Well, it's a package that moves things, where it stands for pretty much anything that has actuators. Initially, ARM navigation was geared for ARMs. This is geared for ARMs as well, but I mean, I guess it's not geared for ARMs. It's geared for any groups of joints that the robot can have. And from a high-level perspective, it does the same thing as the ARM navigation. Given some sort of input, which is typically the description of the robot, and this is really like URDF, SRDF type of data that David was presenting earlier, and optionally sensor data, this thing can produce path plans that typically are sent to client libraries, usually your controllers, but not necessarily. So let me give you an overview of what Move It actually contains. So to begin with, Move It can represent robots. It can represent geometry, so the meshes that are loaded from the URDF. It can represent the links, the joints, essentially the degrees of freedom that you're going to be planning for. And we support mimic joints. This is a new feature that we added, and it's available with the ROS Fuerte. Of course, we parse the semantic robot description as well. And this essentially allows planning algorithms to reason about robot configurations. And if you have things like arms in your robot, then you can do forward kinematics, inverse kinematics with libraries such as KDL or your own custom solvers, whatever you want. Now, an important step in planning is making the decision of whether a state is valid or not. What makes a state one that is okay to be in or one that we should avoid? And in Move It, we define this to be the intersection of two constraints. Namely, the state needs to be collision-free, and it needs to satisfy some additional user-specified constraints. So for the state to be collision-free, that's fairly obvious. Nobody wants robot arms to be overlapping with their TVs. And for that, we use the flexible collision checking library, which was described, I guess, just a few days ago in ICRA. And this is a very nice library. As opposed to the software that we had in ARM navigation stack, a very cool feature that I feel I should mention is that we can actually do collision checking in parallel. This may not sound like much, but it actually greatly increases the efficiency of software that uses this library because you can do multiple things in parallel. You don't have to serialize collision checking. And we can do other things like probability of collision and so on. Now, to complete the notion of a validity of a state, we need to define what it means for a state to satisfy some constraints. And in a general sense, this is really, you define a procedure that's called a constraint evaluator, and given a state, this constraint evaluator will say yes or no. This state is good, this state is bad. It can give you additional information such as distance, but gradients, but that doesn't matter for this point. So MoveIt is, we made an effort to work on the representation, sampling, and evaluation of constraints, and I'm going to talk about this in a little bit more detail in a few slides. But we have some types of constraints, like joint constraints, visibility constraints, and these are already predefined, but the users can specify their own types of constraints. If you have your own robot that needs some sort of, I don't know, balancing constraints, that's fine, you can define those. Using this basic functionality, you can actually implement motion planning. And as Sachin mentioned, we have multiple types of motion planners. And this is implemented all as a generic interface, and we support essentially 3 categories of planning algorithms. The first category is sampling-based motion planners, which we take from the OMPL library from the Kavaki lab at Rice University. We have search-based planning techniques, the SBPL package from Max Likachev's lab, and I believe we have authors from both of these libraries in the audience, so you can contact them later. We also have optimization-based planning, such as Chomp and Stomp. I'm not sure, I haven't seen any of the authors in the audience, but raise your hand if you're here. All right. Once you actually obtain a motion plan, you probably want to execute it or at least visualize it. And it's often the case that some of these planners don't necessarily produce the best quality of paths. I'm sure all of you have seen like very weird wavy arm motions. So MoveIt actually includes a lot of code on optimizing and time parameterizing trajectories. And then these trajectories can be sent to the controller and monitored as they're being executed. So there is software that essentially monitors sensor data. And then if something that shouldn't happen happens, like the arm moves where it's not supposed to move, or the path becomes invalid, then the execution is essentially stopped, trying to get some safety in there. Of course, there's a bunch of nice extras. Well, nice is a personal perspective, I guess. One of the main things is benchmarking. So we realized that while developing the ARM navigation stack, we couldn't even do things like regression testing in terms of performance. So if the performance of a planner dropped, how could we tell? And benchmarking can actually help with this because you can generate a set of benchmarks this week, generate again next week, and compare. Of course, this has other advantages, as I'll mention in a second. We can have storage of planning scenarios. This actually exists in ARM navigation as well. It's been developed by Gil Jones. There's a lot of visualization and debugging tools. So in building this, we actually run into bugs, and we need to fix them. And an approach we're following now is really we're developing the right tools to help us find those bugs in the hope that they will actually be useful for other users. And we also have the automatic configuration tools that Sachin described, and these will be ported. Now, I told you essentially what MoveIt consists of. Let me talk about the architecture for a little bit. So if you have a running system with, say, whatever, Robot X, I like to think of MoveIt as a system that consists of 4 components, 3 software components and a configuration component. So the last one here is really robot-specific configurations. Essentially, they're user settings, but with the existing tools, you can actually generate these settings easier. And the first 3 are software. The first box is really not our software. It's various third-party libraries, such as OMPL, SBPL, Octomap, and a number of other libraries. The functionality I told you about in the previous slides is essentially in the core functionality box, so this one here. And the communication is separated from these core libraries. So everything that has to do with ROS parameters, ROS topics, services, the type of communication that ROS enables is kept separate. And of course, using this is what you really want to do because it's much easier to use and much nicer and everything just works. But we're going for a modular design. We're trying to have everything consist of a bunch of essentially C++ libraries that have lightweight dependencies so that if someone doesn't want to use the whole thing, they can just take library X and its dependencies and just use that. In addition to this, we wanted to make everything easily extensible. So there's this thing called plugin lib in ROS, and pretty much everything we do, well, not everything, but most of the important components that we expect people might want to change are implemented as abstract APIs, like a base class, and then there's a number of plugin implementations for that. So we have generic interfaces for motion planners. We have generic informations for generic API for kinematic solvers, for constraint samplers, and a number of other components. Some key characteristics that we're trying to get with this design are that, I'm just trying to underscore this. So we really want a simple configuration. We really want the user to just come, bring the URDF and SRDF, and then get planning for free. Also, all of this was designed with efficiency in mind. So our code is thread safe. I probably don't care about this, but we were very, very careful about const correctness and things like that. And now, just to underscore again our intention to make this general and generic, I'm showing a demo of MoveIt running on 2 different arms that are not the PR2. So this is the universal arm and the Motoman arm. This one is avoiding essentially self-collision, and this one is avoiding the FedEx box here. This is our standard collision object. If you want to see a demo of this, Gil has it running in the exhibition section, and you should be able to see it play live. So, because I don't actually have time to go into lots of details of like what MoveIt has to offer, I'm just going to give you a sneak peek of some of the features, some of the newer features that were not possible with the old software, but are possible with MoveIt. And these are just these 3, the multiplexing planners, handling generic constraints, and benchmarking. So for multiplexing planners, this is like, we've had lots of discussions with Gil and Sachin and talking about like what can we do, how should we organize things. And a byproduct that's really nice that comes out of the fact we have generic interfaces for planners is that we can multiplex them. So you can define a generic planner that essentially looks like this box, satisfies the same interface as DOMPL, CHOMP, or SBPL planners, it doesn't matter. And then you can actually load multiple planners inside this box, handle planning requests, and then report the plan that was found quickest, or the plan that was found shortest, whatever your constraints are. So this is really flexible. I just wanted to show that a simple application that is actually trivial to do with the current setup. Another thing I really want to talk about is constraints. So this is really important. Everything from goals to conditions that you want to impose on paths are specified in terms of constraints. So if you want to hold a glass of water upright when you're moving your robot or you're delivering a drink, this is actually done with specification of constraints. And we have a couple of standard types of constraints. And joint constraints are obvious. You essentially just limit the space of sampleable values for that particular joint value. Task constraints are, again, fairly obvious. There are position constraints and orientation constraints imposed for particular robot links. So here you typically would do things like inverse kinematics to generate states that satisfy these constraints. And another thing that came out actually out of our calibration process are the visibility constraints. So you might have seen a PR2 sort of moving a checkerboard in front of it, like with a pattern that it can recognize. Ideally, you want it to hold a checkerboard such that it is in the view of the sensor. And those are our visibility constraints. Now, when you actually want to do planning with constraints, especially for sampling-based planning, a key component is actually generating states that satisfy these constraints. And this is not this is an expensive process. So as I said, if you're doing position constraints or orientation constraints, you do inverse kinematics. That's not slow, but it's not exactly zero time either. When you're doing visibility constraints, we're actually doing this with rejection sampling. And it turns out we're throwing away about 99.3% of the samples we generate. So that's a lot of wasted effort. So what we're doing is, okay, we know what the constraints could be, have a set of constraints, produce an offline, do some offline computation, generate a bunch of states, and just store them. So this is a form of learning. It doesn't matter how much time, or it doesn't really matter how much time the offline computation process takes, because we do it once, then we reload the states, and then in the planning process, we reuse this, and we gain a lot of efficiency. I'm not going to go into details on how this works. I just want to show you some results. So this looks like a lot of numbers. Don't try to read them. I'll go through them, or some of them, in a bit. So these are just two different problems with two different sets of constraints. The visibility constraints are actually the ones in this image here, with the checkerboard moving to avoid this obstacle. And the dual arm constraints in the bottom part here are in this particular image, where the robot is holding a tray at a particular orientation. So for the visibility constraints, if you just look at numbers, I'm not sure you can actually see them, so I'm going to read them. On the columns, we have different sampling-based algorithms. And for each algorithm, we report runtime in seconds and success rate for varying sizes of the state database, if you will, the result of the offline computation. And on the top row, we have the method that doesn't use any offline computation, and the method that uses varying sizes of offline computation. So if you just take the first algorithm here, it takes like 0.95 seconds on average. But if you use the database, it takes about 0.3 seconds. So that's a factor of 3. This algorithm takes about 3.9 seconds on average and 0.6 to 0.8 if you use the database. If you look at this problem with the dual arm constraints, remember this is this case, you really have a closed chain here. So there's a lot of inverse kinematics that's being done to compute those states. And here, with the time limits that were actually imposed on the planners, they barely were able to solve the problem. So you get like 2%, 1% success rate even. And even when the planners do succeed, the runtimes are high, like this says 9 seconds. With the database of constraints, this says 0.2 seconds. So this is a significant speed up. Another thing that I'm really fond of is benchmarking. Say you have your favorite robot, and you know what environment you're going to be using it in. What planner should you use? I don't think there's such a thing as a best planner there that can be used for any situation. But for particular situations and particular robots, you could identify perhaps a planner that does better for that particular situation. So if you're in an industrial environment or some home environment, maybe your choices should differ. And we built a benchmarking infrastructure that allows you to run many planners, run them many times, average results, store them in a MySQL database, and we're also putting all of this information online. So this is a print screen of plannerarena.org. You can check it out, but keep in mind this is a website still under construction. And the intention is to have a number of planning algorithms described here, and their performance presented for varying problems. And we welcome here contributions of both planning algorithms and problems, so please send those. What I would hope to see is that at some point, someone comes and says, look, I implemented this my new planning method. It is available in MoveIt, and this is how well it does compared to other planners in plannerarena.org. In terms of data that plannerarena.org includes, this is just an example. So I hope you can see it in the back. This is really just a disk for every planner, where the size of the disk is the memory the planner used. The color represents the success rate. Blue means good success rate. Red means bad success rate, so very low. And the x-axis corresponds to the solution time. The y-axis corresponds to the solution length. If you don't like this type of plots, that's okay. We have bar plots too. So you can just click and get this. This is all Google Charts, by the way. It's fantastic, really easy to use. Ken, I hope you're working on that. That said, I'm just gonna stop talking about like current MoveIt features, and I'm just gonna mention a few new things. Things that we are looking to work on this summer or in the near medium future. One of these is handling uncertainty. So this is in connection to the FCL library, like doing point cloud collision detection and things like that. We want to continue on learning from experience. So if the robot goes to the same area repeatedly, it can remember what sets of paths are valid for that particular area and then reuse them. There's no point in redoing all the computation over and over again. We want to work on planning with dynamic constraints. We want to work on better integration with grasping. So right now, unfortunately, if you ever see the PR2 grasping something, like it's going to come to an object, stop, and then move forward and actually complete the grasp. The last step, the little segment, is actually it's actually a blind motion, and we're trying to replace that with safer computation. We also want to work on tighter integration with sensing. This is actually a long topic, so if you have questions about this, let me know. But one thing that is very interesting to me is to use things like Octomap to figure out where the occluded space is and reason about that in the planning process. This work would not have been possible without the contribution of many, many, many people, and this list is probably not complete. So if you see your name not here, and it should be here, let us know, but hopefully we got some. So thank you all for all your contributions. In terms of like a concluding remark, I'd just like to say that MOVEit is intended to be a platform for application development. You can develop industrial applications, you can develop research applications. We're trying to gain feedback from the community. So if you have suggestions from your experience of using ARM navigation stack, or there are particular things that you would like to see in this, please let us know. We're committed to developing these things and to solving new problems that relate to motion planning. And there's some more resources here on ARM navigation and MOVEit. This is not yet complete in the sense that we don't really have good tutorials and good documentation yet. So we're not really advertising it too much. Also, moveit.ros.org, if you check it out, you'll notice that's a website under construction. But there's many ways that you can contribute, and they are listed here. And at this point, I guess thank you very much for listening. And if Sachin has any remarks that he'd like to add, okay, then I will take questions, or we will take questions.
Actually, one last person I wanted to point out is from Max Likachev's lab, sitting all the way at the back, Ben Cohen, one of our ROSCon volunteers, and he develops the SBPL ARM planners all the way in the back.
Wave at us, Ben. I believe so, yes.
So the question was, does the trajectory optimization have a plugin architecture as well?
And I think the answer is yes. Gil, yes. Gil wrote the trajectory optimization part, but yeah, there's a plugin architecture there as well. Other questions? This was a very clear talk. Yes? What do you mean? So the question is like, so the question is, what is the current ability to do dynamic motion planning? At this point, we are essentially doing quasi-static planning, essentially, as you said, under kinematic constraints only. We do not plan and control space. The planning libraries that we use do have that functionality. In particular, OMPL does include such abilities. Things like Chomp and Stomp do produce paths that are amenable to be sent to controllers, but explicitly we do not support that yet. But I believe Sachin is going to work on that this summer.
Yeah, so it is something we're going to work on this summer. Actually, in Stomp particularly, you can put in cost functions that represent some kind of dynamics in it. And we know some other people at USC have extended it to do some of that stuff, but hopefully by the end of the summer, we'll have more dynamic motion planning in our stacks.
Yes? Excellent question, thank you. So the question was if there's a solution for planning on uneven terrain or essentially where we're not moving on flat terrain. Am I correct? Okay. So remember the previous talk when there were those two joints that we didn't know what to do with, the planar 2D joint and the 6-TOF joint and the URDF? The answer is, well, we don't have examples of this working yet. But those joints, those types of joints are for moving in plane, essentially SE2 space or SE3 space, like with a floating joint. And I believe some people in Freiburg actually are doing planning, like footstep planning with these types of joints. I don't know if Armin's in the area. Okay, so that will be described later, but that is using MoveIt with, I guess, not the usual setup. So.
So it's called MoveIt, so that I could get. Oh, so his question was, why is it called MoveIt and not ARM navigation? And the second question I think was, is it going to break the APIs? It's called MoveIt, so I could get Ioan to dance to that music. No, actually, it's called MoveIt. We sort of brainstormed the name, and there's a software called Graspit that does grasping. And so from that, we got to MoveIt. We didn't want to call it ARM navigation because we were moving beyond ARMs, and we were getting to, we're looking at doing full body planning and things like that. So we wanted it to reflect what we were actually doing. In terms of the API, it will break the API, is the gist of it. I'm sorry about that. We really wanted to try and not do that, but when you evolve software like this, at some point, the previous API can become, not so. It's hard to keep it. We'll look into solutions so that maybe there's like a bridge so that we can maintain some kind of API stability. The one thing, though, is that the ROS API that we have, it will break it, but the actual core of what it does will stay fairly constant. So we'll look into a solution so that it's not a complete breakage.
So just to complete this, I guess, you're probably going to be able to fix your code by just doing search replace. So hopefully that's the case. If you're using ROS level stuff. If you depend on C++ functionality, I'm sorry.